Good day, students. Today we will look into X-ray diffraction. It is a non-destructive technique to study materials. To understand X-ray diffraction, we first need to recollect a few terms. That is, we need to remember what a crystal is, we need to know what X-rays are, and we need to remember what is diffraction. Now, a crystal is a solid material that is having certain properties. Okay. So it is a near perfect material. In it, the atoms or molecules will be arranged in a repeating manner. They will have a definite geometric pattern, right? They will have long range order. There are some properties, that is, they have sharp melting point and also their isotropic nature. It will be anisotropic in behavior. So these type of solid materials, near perfect repeating arrangements of molecules will be seen in it, and they are called crystals. A few examples are sugar, snowflakes, and diamonds. Now, we all know about the electromagnetic spectrum, and here X-rays are a part of this EM waves. So it is a form of this electromagnetic radiation with the much shorter wavelength side. Okay, so its wavelength is much shorter than that of the visible light, and it ranges from 0.01 to 10 nanometers, 10 raised to minus 9 meters. These X-rays are usually used to study about materials, very small materials, materials that cannot be seen with a regular microscope. So in order to study about its structure, we use X-rays. And light, here the X-rays, when they fall upon these crystals, they will undergo the optical phenomenon of diffraction. Now, what is diffraction? So when EM wave, it falls or hits an obstacle, or it passes through a aperture, very small aperture, the wave will bend. Okay, so it will bend in some direction, and there will not be any change in its wavelength. Okay, so these are the terms that we need to recollect in order to learn about X-ray diffraction. In X-ray diffraction, the people who study materials using this technique, they are usually called crystallographers. They study crystals. So they use X-ray diffractions to produce different diffraction patterns on a screen, on a detector or film. And then these patterns are later on, they are studied, they are analyzed to understand the arrangement of the atoms or molecules within that particular crystal. So here in this picture, we can see that we have this X-ray tube here. Okay, so this is the source of X-rays. It will produce X-rays, and these X-rays are allowed to fall upon a very small aperture. Now this aperture, it is used here just to reduce the beam size. Okay, so here we have a very much broad beam, a spread beam, divergent beam that is made into a very narrow beam here using this slit. Okay, now hence this narrow beam of X-rays, it is made to fall on this crystal. The crystalline solid is placed here. It is the target object, and when X-rays fall upon this crystalline solid, light, or here X-rays, will diffract. It will undergo diffraction, and based on the structure of that crystal, it will form a diffraction pattern on this screen here. Okay, so right at the center we will have that spot from the X-rays coming directly from that X-ray beam. But surrounding that, we have the spot from the diffracted X-rays. And all of this can be recorded upon a detector or a photographic plate. Now, to get information about these crystal structures, we are looking into the crystal structure of dimension angstroms, right? 10 raised to minus 10 meters dimensions. We have to study about that. Now, diffraction occurs when the spacing of the crystal is of the same order as the wavelength of light. Okay, so this X-ray diffraction pattern is used as a standard fingerprint technique for crystal identification. Okay, so only X-rays can be used to study crystals because of the requirement that in order to diffract the X-rays, the crystal dimensions or the target object should have a dimension of angstroms. It should be in the dimension of the wavelength of that X-ray. Here the crystal thus acts as a space grating. It is not a plane grating, it is a grating in 3D space. X-ray diffraction also provides the most definitive structural information about interatomic distances and bond angles. So here, first we saw that from X-ray diffraction we get an idea of the structure within the crystal, the structure of the crystal, and along with that we get an idea about the interatomic distances between the atoms and about the bond strength and the bond angles between these atoms or molecules. Now, in order for diffraction to occur, we have to look into a few particular things. Now, when a wave hits an obstacle or aperture, three possibilities are there for the light to behave based on its wavelength and the spacing between that scatterer or the aperture size or the obstacle size. If the wavelength is very much less than that of the obstacle or the aperture, here light will get mostly transmitted through it. Okay, so the aperture will be large compared to the wavelength of light. So light will transmit through it. Now, if the wavelength of the light is comparable to the size of the obstacle or the aperture, here light will hit on it and bend through it. Okay, so if light passes through a aperture of similar dimension of its wavelength, it will diffract through it. Or when light falls on an obstacle of dimension in the range of its wavelength, it will diffract over it. Okay, so here diffraction takes place. And the next case, if the wavelength of the light is very much greater than that of that object or the aperture, the possibility is that reflection of that wave takes place. Okay, so if that object or the aperture is very small compared to the wavelength of light, light will fall on it and get reflected. So here we understand that if the wavelength of light is of the order of the lattice spacing in the crystal, then diffraction effects will be prominent. So, since crystals have a lattice spacing of the order of angstroms, we take the EM wave of angstrom wavelength, that is X-rays, for diffraction to take place through the crystal and hence to get the pattern, a diffraction pattern from it. Now let us see what happens in X-ray diffraction. When X-rays, they fall on a crystal, here we have this X-ray tube, it produces X-rays and these X-rays are allowed to pass through a slit. So this slit makes this beam into a narrow beam. That means it collimates light, hence it is called the collimator. Okay, and it is made of lead, hence it is called a lead collimator. And the narrow beam from this collimator is made to fall on the crystal. The crystal then diffracts light and hence forms a diffraction pattern on the photographic film or screen. Now this pattern is called the law pattern. It is called so because of the scientist who first suggested its possibility. Now, this law pattern, it shows the symmetry of the crystal. Here below, this is the law pattern. It is one of the law patterns, diffraction patterns. And in this pattern, you can see the similarity of the spots formed by the X-rays. This similarity or these spots, regularly arranged spots, are formed because of the regularity within the crystal. Okay, so if the crystal is a pure crystal, it will produce a diffraction pattern as such. And hence this pattern reflects the symmetry of the crystal. Now, it was Max von Laue who first suggested that it is possible to create a diffraction pattern from a crystal using X-rays. So this crystal serves the purpose of a grating. And this was first experimentally demonstrated by his associates Friedrich and Knipping. They demonstrated the diffraction of X-rays from a thin crystal of zinc blende. Here the position of the XRD peaks, X-ray diffraction peaks, is related to the nature of the crystal's structure or crystal lattice. Here in this pattern we can see that there are spots, right? These are the X-ray diffraction peaks. The distance between these peaks, its arrangement, is all depending upon the nature of that crystal lattice. It can be cubic, it can be triclinic, it can be orthogonal, it can be triclinic, it can be hexagonal. So depending upon that, we have the position of the XRD peaks. The intensity of these peaks is related to the type of bases in the crystal lattice. So we have different peaks here, and the intensity of each of the peaks, that is dependent upon the nature of the bases, right? That is the nature of the atoms or group of molecules based in the lattice points. Now this is a father-son pair. It was these two people who put forward a model that could explain the X-ray diffraction. They came up with Bragg's law. So this is the father-son duo, William Henry Bragg on the left side and William Lawrence Bragg on the right side, who could successfully explain X-ray diffraction. Now, in this model here, the crystal lattice is assumed as a set of parallel planes, and each of the plane is having a spacing, interatomic spacing, interplanar spacing of small d. Now, when light falls on a crystal, few rays fall on the surface, other rays penetrate to the first layer beneath it, then the other rays penetrate to the second layer beneath it. A few rays will penetrate into the different layers and get diffracted from these different layers. And these diffracted beams, they superimpose or they interfere to produce the diffraction pattern. So here theta is the glancing angle. It is the angle between the surface of the crystal and the incident ray. Okay, so the angle between the crystal surface and the incident ray is called theta glancing angle. Small d is the interplanar spacing. In Bragg's method, the diffraction is visualized as reflections from a set of planes. Okay. Now here the crystal is a collection or an aggregate of a large number of parallel planes. And when X-rays are falling upon it, they get reflected from these parallel planes and they undergo constructive interference to form a diffraction pattern. Now in this figure, we can see that the first ray is falling on the surface at a glancing angle of theta and getting reflected upon it. Then, if this angle is theta, the angle of incidence will be 90 minus theta, right? Again, angle of reflection will be 90 minus theta, and hence the remaining angle will be theta. Okay. Now the second ray will get reflected upon the second plane in a similar manner. Now here this angle will also be theta, that is the glancing angle on the second plane is also theta. Hence the remaining angle here, it will be 90 minus theta. Now consider the triangle AOB. Here angle B is 90 minus theta, angle A is 90 degrees, and hence angle AOB must be theta. Okay. Likewise, angle COB will also be theta. The path difference between the rays reflected from nearby or adjacent crystal planes is calculated by drawing these normals A, O and CO from these two waves. So this will be the additional path traveled by these two rays. Okay. Hence, the additional path AB plus BC is calculated as 2D sine theta. Now, how do we arrive this? AB is calculated by using the sine theta. The sine of theta is given as opposite side by hypotenuse, that is AB divided by small d, interplanar spacing. Hence, AB is equal to d sine theta. Likewise, here sine theta gives CB by small d, that is CB is equal to d sine theta. Thus, AB plus BC will be equal to 2 times d sine theta. Now, for constructive interference to take place, the path difference between the interfering waves should be an integral multiple of the wavelength lambda. Okay. Hence, the path difference here is 2d sine theta. Thus, if n lambda equals to 2d sine theta can be satisfied, where n can have values 1, 2, 3, etc., any integer value. If this condition is satisfied, we will see a diffracted beam in these positions of theta. Hence, this condition n lambda is equal to 2d sine theta is called the Bragg's equation. It is this equation that explains X-ray diffraction. Now, in X-ray diffraction, for different values of theta, the intense reflections at different directions is obtained, right? So for different theta values, different positions can be satisfied. Okay. So for the first case where n is equal to 1, we get the first maximum at sine theta 1 is equal to lambda divided by 2d. Okay. Now for the second maxima, we get sine theta 2 is equal to 2 times lambda by 2d. Again, the third maxima obtained at sine theta 3 is equal to 3 lambda divided by 2d. Hence, we can see that we get different diffraction beams or spots depending upon the integral value of n. Also, the intensity of this diffracted beam will decrease as the order n increases. In this figure, it is evident. So here, the intensity of the diffracted beam is very high. It is maximum. Whereas, if you move away from the center, here what happens is the order of the spectrum will increase. So as the order increases, the intensity of that diffracted beam is seen to decrease. Now, at certain angles, the Bragg reflections, they reinforce to produce a maximum intensity. So at certain points here, okay, at here, this position, at these positions, at these positions, and at these positions, we can see that the diffracted beams are again, they are sort of combining together. They are reinforcing together, okay. And there again, we get a higher maxima. Whereas at other angles, these Bragg reflections, they cancel out to produce zero intensity or feeble intensity. Likewise, in these regions, okay, so in certain regions, they appear to cancel out in these regions, again here, 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 sort of here, here, they appear to cancel out. Okay. So again, there the diffraction intensity is very small or almost zero. So in this pattern, we can see that there is a regularity, there is a repeated nature in this pattern. And this is a proof that the crystal has a definite structure. And from these patterns, we have been able to understand the structure of crystals. We have been able to decode, we have been able to model the exact structure of the crystals. We can learn about the nature of the interatomic bonds and their bond strengths. And all of this is possible using these XRD patterns. That's all for today. Thank you.